we're going to perform 3 equilibrium problems that utilize an icebox. And an icebox is an easy way to do more complicated stoichiometry. So let's take a look at the first one. It says a mixture of 3.2 moles of N2 and 3.2 moles of H2 are sealed in a 1 liter container and heated. When equilibrium is reached, the container holds 2 moles of NH3. Calculate the K for the equilibrium equation below. It is very important to understand what you know and what you don't know. So when it says calculate the K for the equilibrium, that means that you don't know the relationships between the products and the reactants. But that also means that you must, based on the information you know, be able to determine all of the equilibrium values to be able to get to a K. What do I mean? Well, K, the equilibrium expression would be this. Right? Ammonia squared over nitrogen times my hydrogen concentrations, and my hydrogen would be cubed based on the coefficient. If I want to solve for K, I need all 3 of those values at equilibrium, right? I need my concentrations at equilibrium. Otherwise, I can't solve for K. So the values that are given to me within this problem, I must be able to determine that. So if I use an icebox, and it says that I have 3.2 moles. Now, in an icebox, you can use moles or you can use molarity. The key to this is that there's a liter. So I'm going to instantly go 3.2 molar and 3.2 molar. It doesn't tell me how much ammonia I start with, so I assume it's 0. Because it's 0, I know that my reaction is going to be moving to the right. So because of that, I know that I'm going to be adding. This is going to be subtracting. This is going to be subtracting. What does it subtract by? By the magnitude of the mole ratios. So in this case, there's one of these. There's 3 hydrogens, and there's 2 ammonia. There was one more piece, though, that they gave me, and it was this right here. It says, when equilibrium is reached, the container holds 2 moles of ammonia. So that means I know that I already have that amount. So the minute that that has happened, what has occurred is a real simple but very important algebraic relationship there, right? 0, from 0 to 2, there's a change of 2x. So I can solve for the very fact that x must equal 1.0, right? So by doing that, I can now plug these 2 other values in. So 3.2 minus x ultimately is 3.2 minus 1, right? So I get 2.2. And the same thing here. So magically, I have now solved for my equilibrium values. If I have all 3 equilibrium values, now I can solve for K. So if a problem is ever asking for K, you need to recognize that you must be solving for all of your equilibrium values before you can plug it in. So now I just simply plug in the appropriate numbers. And that would be my K value. And that K value shows that my reactants are more favored than my products. So, classic problem of solving for K, recognizing that you must be able to fill out all of your equilibrium values in your icebox. Next problem's a little different. So let's take a look at it. So first, it says that I have, sometimes it's just about writing down what you know. It says that I have 5 moles of H2. I have 5 moles of CO2. And it's placed in a 4-liter container. Okay, that's going to be a problem for us because it's not a liter and they gave me moles. Why am I saying that? It's because ultimately, 2 things. 1, it says that I'm looking for concentration. 2, if you're ever plugging it into an equilibrium expression, those expressions either need to be, if it's a Kp, a pressure, or a concentration. So what I'm going to do before I even start an icebox is I'm going to actually convert this into molarity right away. It's not necessary, but it's going to make my life easier for later. So by doing that, I get 1.25 molar and 1.25 molar. So that is my beginning of my icebox. So here are my values. I am assuming that I don't have any of my H2O and my CO. It did tell me that my K is 0.88 already, right? Which will ultimately equal my equilibrium expression, which usually is asked at some point in a problem. So if I have my K, that means that I will not probably know my equilibrium values immediately. I will have to plug it into my equilibrium expression. So let's see how that looks. Because these are zeros, the reaction is going to be driven to the right. So this is plus x, minus x. So I have 1.25 minus x. And those are my expressions, my equilibrium expressions. So these can be plugged into my equilibrium expression to the right here. So K, which is 0.88, equals x times x over 1.25 minus x times 1.25 minus x. Okay, this is a very important problem to recognize, is that when you look at this, x times x is x squared. But 1.25 minus x times 1.25 minus x can also be written using that as a squared. So ultimately I get this. Well, what's the big deal about that? Well, now I can actually solve for this problem quite easily. I'm going to take the square root of the entire problem. And because of that, square root of 0.88 is 0.938. And then the exponents vanish. So that's my first part of my expression there. And then we can start to distribute. Right, so what I can do is I'm going to multiply this expression to the other side. So I'm going to show every single step. If you understand this, absolutely fantastic. So we're going to start way over here, just so you can understand what I'm doing. So that would be my first step. I distribute this out, right, to both values. I get 1.1725 x minus and that is not an x, I apologize. Combine like terms, so add the x to the other side. And then divide it out. And I find that x is 0.605. Okay, now we need to make sure that we revisit the question. The question is, calculate the concentration for all the species. These are the relationships right here. So at equilibrium, the products are x, and the reactants are 1.25 minus x. So understand that two of these equal the same, and the other two equal the same values. So I'm going to write it as so. My reactants are H2O and CO. Sorry, my products, and my reactants are H2 and CO2, and those both have the exact same expression, so I'm going to solve it at the same time. So this equals X, which simply equals our value, and the other value was 1.25 minus X. So if you subtract that from the other, it will become 0.645 molar. So those are my concentrations at equilibrium for all 4 species. And we did that by taking the square root of both sides and then extrapolating that out. This last problem is easily the most difficult one. It says the reaction represented by the equation below is at equilibrium in a container with, and then it gives you the amounts. So let's do that right away. I'm just going to organize my information. It says how many moles per liter of H2O must be added to increase the concentration of hydrogen to 0.7. Okay, what you have to realize is that all reactions will reach equilibrium. When you add or you subtract, it will continue to fluctuate other values. So I'm going to need an icebox. Here's the problem. Are my values that I have right now an E? Because if it is, then where do I go from there? Because the E is kind of the ending point. Well, we're changing the ending point because we want to change the amount of H. So I could begin, but what I don't see is a K. Please understand, either you have to have concentrations at equilibrium or you have to have a K. If you don't have either one, you cannot find anything at equilibrium ever. So what do we have at equilibrium? Well, these are currently at equilibrium. So what if I actually plug that in to the K value, the K expression? So if I have this expression already, and I'm asked for the generic relationship, because it's already balanced, here it is, well, I can just plug these values in. So by plugging them in, it actually tells me that K equals 4, which sometimes is an uncomfortable value because it doesn't quite seem like that would be an appropriate value, but K's are 4, so that means that the products are favored. Okay, so now what you need to understand is that these are no longer my equilibrium values. This is my I. This is my initial. Why is that? Because at equilibrium, we want our hydrogen to be 0.7. So that is the other information. So you got to allow the icebox to give you information. So that is giving me some information. So what I could do, I'm going to do it in red right here, very small, is that clearly I'm adding because it's going up. So it's going to be going this way. So this is plus X and minus X and minus X. But if you look at that, this gives me a clear indication of what X would be, right? So this would be 0.1. So plus 0.1 plus 0.1. So my value is already 0.3 minus 0.1 minus 0.1. So my value here is 0.20, and my value here is 0. Right? That's 0. Well, that can happen. So the question is, how many moles, which we are in a liter container, of H2O must be added to increase H2 to 0.7? So I would have to be able to add in a certain amount of this to get to this value right here. So what I'm going to simply do is call this X. I don't know what that is. And I'm going to allow the expression to help me. So we're going to plug it in to the equilibrium expression. So give it a shot, solve for X, see what you get on this. you solve this properly, you would have determined that you needed to add 0.263 molar of your H2O to reach this equilibrium. Again, all these values on the E line have to have a relationship plugged into the equilibrium expression that equals the determined K. And if K is 4, then that's going to tell me that my final concentration, my H2O, is going to be 0.263, which is the amount that would have been needed to be added to the H2O to drive this reaction to the right to produce 0.7 moles of H2.